Probably, so you've had a bunch of integration by parts recently, but probably on the next quiz I will put an integral involving products of the powers of cosine and sine, where at least one of them is on, like the example we did last class period before the new test. So make sure if you need to review that, that you do that before the next quiz. Okay, I did finish the problem up here, and I circled the final answer in green right there. That is a formula for the distance traveled for this parametric curve. Such a simple parametric curve, too. Look at that. Such a simple parametric curve leads to a very complicated formula for the distance traveled. But at least it's something that can be found, okay? That's nice. I'm glad we were able to find it eventually. How did I finish the problem? Remember, before the quiz, we were over here. That was the answer in terms of theta. And then we needed to use the fact that theta is the arctangent of 2x to get back in terms of x there, but then ultimately tau here. Tau plays the role of x here. Tangent of theta was 2x, so where I saw tangent theta, I replaced it with the 2x there and there. The 2x here, the 2 canceled with the 1/4 to leave a 1/2. And that tau is like the x. Secant theta got replaced with square root of 1 plus 4x squared, square root of 1 plus 4 tau squared. Then I got 1/4 natural log of the absolute value of 2 tau there is like a 2x, that would come from that one. And the square root of 1 plus 4 tau squared comes from that one, because secant theta was that. Back and forth here. Tracking with me? You got to follow where my hands go, okay? Not everybody's looking up here. Oh, that's so good. This gets evaluated. Tau goes from 0 to t. It does turn out that both of these end up being 0 when tau is 0. That wasn't a guarantee, but it did happen. That's 0 when tau is 0. This is 0 when tau is 0 as well, because you get 0 plus 1. When tau is 0, you get square root of 1. We know natural log of 1 is 0. So you only need to make the replacement of tau with t to get the final answer. What's the graph this look like? I think I can graph the basic picture without technology. I know it's got to go through the origin, and it's keeping track of the area under the speed graph up to any moment in time. So it's got to be increasing. I mean, my distance traveled has to be increasing. It's got a slope equal to the value of the speed graph at 0, which was 1. The initial slope is 1. The graph of the distance traveled in green here is going to look like that. I can graph that without technology. I don't know where these are going to cross, and it's not such a big deal where they cross. It doesn't matter when the distance traveled equals the speed numerically. They're different in terms of their units. Distance traveled, say, in meters, and speed in meters per second. It doesn't really matter where they cross, and I don't want to bother finding where they cross. Probably they eventually do cross. I guess I'm not positive that they cross. Okay, I need the technology to know whether they cross or not, but it's not a big deal. That's the point. I checked this stuff on Mathematica. How did Mathematica do the integral here with involving x? They wrote the answer differently. What? Arc sin h? Is that an h? Yeah, it is actually. That's another typo. That's a inverse hyperbolic sine. Have you ever heard of hyperbolic functions? Sinh and cosh. A few of you. 4 or 5 of you. Actually, hyperbolic functions, sinh, cosh, tanh, that have h's at the end of them, are actually disguised forms of exponential functions. But they behave like trig functions, kind of, which is why we write them kind of like trig functions. So if those are kind of like exponential functions, I guess arc sinh or arc cosh must be kind of like a logarithm. And evidently, 1/4 arc sinh of 2x equals that with an x instead of a t. it does involve a logarithm. What about if I just differentiate my answer with respect to t? It doesn't look so good at first, but if I do my simplifying, then it looks good. That's right. I feel good.
Out of curiosity, why would it give that whole big equation?
Because it just didn't simplify. It used the product rule and the chain rule and just didn't bother simplifying, I guess, for whatever reason. Okay, so it is parametric curves. What about vectors? Okay, get to vectors. Let me just say, we'll talk more about vectors on Friday, that as this object moves through the plane along a very simple curve, I mean the curve here is y equals x squared, since x is t and y is t squared, that's the curve. This is a parabola there. That's the curve of motion. You can have a position vector just like with the planets. An arrow pointing from the origin to the location of the object as it moves, as it traces out the curve. So that position vector keeps track of the position of the object. And you can also have something called a velocity vector, which at any moment in time, like this moment in time, points in the direction of motion at that instant in time. It's tangent to the curve. You didn't draw that super well. And its length is equal to the speed. So since this object's speeding up, the velocity vector gets longer and longer. So we'll bring those kinds of vectors into play on Friday when we discuss this more. For the remainder of class, though, I think it would be good to do, well, two things, I guess. We need to look at this Mathematica homework quickly. Overview Mathematica homework number 1, which you're going to turn in online by Friday. And see how far we can get with more trig substitution examples. I still have to put up the assignment, by the way, on Moodle. I haven't done that yet. Going to work on that around, should be able to be working on that by, get it done by 2:30 today. I'll get the assignment up. What does the Mathematica assignment look like? You'll download it off of Moodle. It will look like this. The videos, the extra videos that I want you to watch are supposed to be helpful for this, doing this assignment. So I'm wanting you to learn some Mathematica here. Enough to do these assignments, enough to understand Mathematica well enough that you can be a good user of it in future classes, and enough that you can learn enough to do an exam problem or two, where I'm going to have you write Mathematica code in 1 or 2 exam problems on the first exam. Okay? It'll be related to these homework problems, homework assignments here. There's 2 exercises to do. First of all, you can work in groups, by the way. You should put your names in this spot. Oops, sorry. You should put your names in the spot where it says names, and also rename the notebook with one person's last name at the beginning of the file name. You get points for doing these things, 1 point for renaming the file, and 1 point for including everyone's name in the spot. Although, if you don't put everyone's name in the spot, not everybody's going to get credit for the problems to begin with. So make sure in your group of 2 or 3 people, you can work by yourself if you want to, that you put everybody's name in there. There are 2 sections of this class. You can work with the other section too. You can work with people in that section. But I would put my name here, Bill Kinney, just like that. Just type it. Here's exercise 1. You're going to be using manipulate and parametric plot in Mathematica to make an animation of a motion that's going to start at the point 5,7 when time is 0 and end at the point -7,2 when time is 1. And the videos help you understand how to do that. You'll put your code in the space below. You can enter it to make sure it works, but you don't have to keep the output there for the grader to grade it. The grader is only grading your code itself. You're going to want to define functions f of t and g of t in the way I've shown you before, with underscores after the variable and colon equals when you first define the function. Actually, I'll go ahead and tell you the answer here. Okay, but you should be able to figure it out from what I tell you in the videos. X goes from 5 to negative 7, down by 12. As t goes from 0 to 1, so the rate of change of x with respect to t is going to be negative 12. You can use a linear function here, and it starts at 5 when t is 0. F of t is going to be negative 12t plus 5. G of t is the y-coordinate. That starts at 7 and goes down to 2 in 1 unit of time. Its rate of change with respect to t would have to be negative 5. And it starts at 7. G of t is going to be negative 5t plus 7. Those are two linear functions that will combine to give you a parametric curve, which is actually a straight line in this case, going from the point 5, 7 down to the point negative 7, 2 in 1 unit of time at a constant speed. You'll ultimately use, again, manipulate and parametric plot in ways I show you in the videos to model this motion and to animate it. We'll see the motion. You'll have to figure out what goes inside these things here based on the videos. Okay. Once you get that working, there's a second exercise. This one, you don't have to do any Mathematica code, you just answer the question. Write your answers to these questions in text mode. The directions say you can go to the Format menu, go to Style, and Text. Or you can just do Alt-7 on a PC. I think it's maybe Apple 7 on a Mac. Command button. And now you can write text. The person, you should give brief reasons, like by the Pythagorean theorem is part of your reasoning here. Blah, blah, blah. You can get equations in here by using the palette, the basic math system, which you can get from the palette menu. You can get this thing, and you can type formulas. For example, you can get square roots in there like that. And click on them to do whatever, 4 squared plus blah, blah, blah. Okay, I'm not saying that's the answer. You can do those kind of things in text mode. Write your answer. Highlight your answer in blue too to emphasize it's your answer. You can actually just go over to the cell itself and go up to Format, Text Color, Blue. Get the answers done. Just to make it clear to the grader that you did it. What's great. Okay? So again, the videos are supposed to help. In fact, if you watch the first 6 videos as I told you to, you should be able to do it already. If you understood what was going on there. If you didn't watch the first 6 videos, you're behind by quite a bit because I'm going to want you to watch another 6 here before Friday. There won't be a ton of problems to do from the book. Okay? So the videos I know are time consuming. Once you understand the videos, this is actually pretty quick. And then there's the book problems, which there won't be too many of. All right, the time we have remaining, which is not long now, about 12, 13 minutes. Let's do more integrals with trig substitutions. I've got 3 examples here, but I don't think I'm going to get to all 3. Let's see how far we can get in 12 minutes. All right, let's try this first one. I'm going to go right there. This also involves a square root, just like this integral did. Though now the square root is in the denominator instead of the numerator, and it involves a subtraction in there instead of an addition. the trig identities that are the Pythagorean identities, cos squared plus sine squared equals 1, and 1 plus tangent squared equals secant squared, those are the ones that are useful again for these problems. When you have a minus sign like this, it turns out a good substitution to do is to let the variable quantity that's being squared equal sine theta this time instead of theta. Although, because of the 4 there, I forgot that. Because of the 4 there, I'm actually going to let it equal 2 sine theta. Because I'm going to want to use the fact that cos squared theta plus sine squared theta equals 1, and therefore 1 minus sine squared theta is cos squared theta. By letting x equal 2 sine theta, x squared will be 4 sine squared theta. 4 minus 4 sine squared theta is 4 times this, meaning it's 4 times that. And that'll be good because then I'll get the square root. I'll see that. So I'm going to let x equal 2 sine theta. Not sine theta because of the 4 there. 4 is 2 squared. You want to put the thing that's being squared there in front of the sign in this case. It's tricky. Okay. Then dx is 2 cos theta d theta. And again, 4 minus x squared is 4 minus 4 sine squared theta, which is 4 times the quantity 1 minus sine squared theta, which is 4 cos squared theta. You'll be able to replace the thing under the square root with 4 cos squared theta and then take the square root. And maybe that will lead to good things happening. Let's do it now. I want to use this orange one, that doesn't work so well. Don't forget about the x squared there. If x is 2 sine theta, question?
Question about, so when you have 4 minus x squared equals 4 minus 4 sine squared theta, how do you get rid of the x squared?
Because x is 2 sine theta, x squared will be 4 sine squared theta. So replace the x squared.
Oh wait, you weren't setting it equal to, that was, you were replacing it.
I was using the substitution that I'm doing.
Gotcha.
This is tricky. You just kind of have to learn by experience. When you have a minus sign there, you're going to have a sign involved. When you have something squared there, whatever's being squared goes in front of the sign. That's the trick to knowing this is the thing to do. And ultimately, this is the thing to take the square root of, which will turn out nice. But don't forget about the x squared there. X is 2 sine theta, so we're going to get a 4 sine squared theta here before we write the square root of 4 cos squared theta here. And also dx gets replaced by, I made a mistake there, I forgot my d theta, gets replaced by 2 cos theta d theta. Now this looks pretty nasty, but it's not too bad. It's going to simplify pretty nicely. Technically speaking, we can assume the theta is between negative pi over 2 and positive pi over 2, where the arcsine function can be used, ultimately, so that the cosine of theta is positive, the angle's over in the first or fourth quadrant. And with the square root, I don't need to worry about the absolute values. Okay, that's nice. Whenever you don't have to worry about absolute values, it's nice. So this integral becomes integral of 1 over 4 sine squared theta. Take the square root of that. You don't have to worry about absolute value signs. Don't forget about this. And almost as if by magic, this works out pretty nicely. The 2's cancel, the cos thetas cancel. You're left with 1/4 times the integral of 1 over sine squared, which is best thought of as cosecant squared theta. And that actually is an integral you can memorize. You don't have to memorize it for the gateway, but we could have had you memorize it for the gateway. Just as the integral of secant squared theta is tangent theta plus c. So the integral of cosecant squared is negative cotangent plus c. So this becomes 1/4, well, negative 1/4 times the cotangent of theta plus c. Now get things back in terms of x. X equals 2 sine theta, so theta is arc sine of x over 2, or if you prefer, inverse sine of x over 2. Those are the same thing. And we are in the domain for theta where those exist. And now we need to take the cotangent of that angle. So again, I think it's helpful. You don't have to do this, but it's probably helpful to draw a right triangle. Label one of the non-right angles with theta, which in this case is arc sine of x over 2. You know that the sine of the angle then is x over 2. Sine of an angle in a right triangle like this is opposite of right hypotenuse. So you can take the opposite side to be x and the hypotenuse to be 2. You also could take the opposite side to be 2x and the hypotenuse to be 4. It doesn't matter, as long as the ratio is x over 2. You've got to take the cotangent of this angle. Tangent is total opposite over adjacent. Cotangent's got to be the opposite way, adjacent over opposite. This over that. So you've got to figure out this side. With the Pythagorean theorem, you can figure it out to be square root of 4 minus x squared, which matches that. That happened with the other problem too. We got a match. Except it was the hypotenuse with that other problem. So the cotangent of this angle, tangent is total opposite over adjacent, so cotangent is adjacent over opposite, this over that. Square root of 4 minus x squared over x plus c. That should be the answer. Let's check it by hand. Differentiated with respect to x. Use the quotient rule. You like at least? Good practice. Low d high, the derivative of the top. The derivative of that, you use the chain rule. You get a 1/2 4 minus x squared to the negative 1/2 times negative 2x. Chain rule. It's all part of the quotient rule, though. That's the bottom times the derivative of the top. I say low d high. Minus high, the top. D low, the derivative of the bottom is just 1. That's an x there. Divided by the square of the bottom, the square of what's below. Hopefully that simplifies to this. Does it? Let's see. I like the x squared down there. Let me leave it down there like this. Let's combine these things by getting a common denominator. When you have something to the negative 1/2, that's like dividing by the square root of that thing. So I think I'm going to want that in the denominator. I'm going to get these 2's cancel, but I have a negative sign there still. I get a negative x squared over square root of 4 minus x squared. Move that cursor. Zoom in on this stuff. And then get the same denominator here. That's going to make the square root on top go away. I can now write those as one fraction with the same denominator there. And I do get cancellation of the x squareds. Negative x squared and then a plus x squared cancels, leave me with a minus 4. The minus 4 cancels with the negative 1/4. I think I got it. Yeah, this simplifies to positive 1 over x squared, square root of 4 minus x squared. It worked. Gotta be good at algebra in this class too. Give me that time. Oh, almost done. Let me just say what the substitutions would be in these other problems. I don't want to have to finish them. In this problem, it's kind of like the other problem that we did. You know, we've got a plus sign in there. Except the coefficient of x squared is 1 in this case. So we're not going to let 2x equal tangent theta. We're going to let x equal something involving tangent theta. Because 25 is 5 squared, it'll be good to let x equal 5 tangent theta with this problem. And dx would be 5 secant squared theta. With this one, you've got a minus sign there, but it's not in front of the variable squared. Because of that, it turns out to be best in this case to actually let x equal 5 secant theta. And dx would be 5 secant theta d theta, secant theta tangent theta d theta. That turns out to be the best thing to use for this last one. See it there? That is it. I would encourage you to try these after class sometime before you start the homework. They're definitely doable. Okay, you can work them out. I think I will type up the answers in another Mathematica notebook, but you should try them on your own sometime before you start the regular assignment. Okay, have a good day.